Hello everyone. So for this week, our topic is order statistics. So you would have known about it in some form, but we will discuss about the generic problem and what would be an efficient algorithm for solving that. So let me define this problem. So what is that? So I define the ith order statistics of a set of n elements. So it is the ith smallest element. Okay, so the setting is that you are given n elements, and so you are given n elements, and you may be asked something like, okay, find the uh, fifth order statistics, let's say. So that means fifth smallest element. So what we are very familiar with is something called what is the minimum of a set of elements, right? So for example, so if you find the minimum of a set of elements, so this will be the first order statistics. You can say I is equal to 1. Okay. And similarly, maximum you can say is the nth order statistics. Okay. And again, something that is very, very popular is called median. So median is like the halfway point. So median is the halfway point of the set. So how do you compute median? So if n is odd, then you have the median at n plus 1 by 2, right? If there are 5 elements, median is the third element. And if n is even, then there are 2 medians. So one is n by 2, another is n by 2 plus 1. And generally what you do, you take an average of these. Okay. Now, so this makes the problem setting quite familiar, that we have been doing this, finding the minimum, maximum, finding median. So, but what is the most efficient way we can do it? So we start by making some assumption like the set contains distinct numbers, so that you don't have issue about the fifth largest, so that they are unique elements, so you know, okay, this is the fifth smallest element. So, so we assume that the set contains distinct numbers. Okay, so then we can formally specify this as a selection problem. So we formally specify the selection problem. So your input is set A of n. So here we are saying the distinct numbers and an integer I. And we know I would be between 1 to n. And your output would be the element x in the set A that is larger than exactly I minus 1 other elements. Okay, limits of it. Now, once this problem setting is clear, your input is a set of n distinct numbers, and you have to find the ith smallest that is larger than other I minus 1 elements of A. So how would you solve this problem? So one very simple way of solving this would be, yes, I will say I will just sort these elements. So one possible solution is to sort the elements. And for that, you can use any algorithm. They are not integers, so you can use any comparison-based algorithm like heap sort or merge sort. And once you sort them, you can find the ith element. So, and simply return the ith element in the sorted array. But what will be the complexity? It will be order n log n. Right? So that can be one solution. What can be some other solution? So So we are quite used to finding things like the first largest or second largest. So if you are, or the first is smallest. So if I is equal to 1, so I know a linear time algorithm. So I have a linear time algorithm. Finding the minimum element. And if I is small, I can again keep on doing that. If I is equal to 2, I can run it again. So I find the minimum, then I find the second minimum, right? So that would be just uh, n plus n, right? So it's just lower n. And similarly, if I is equal to k, I can do it in order k. So if k is like k is smaller than O log n, then I think you can just go for this approach. So keep on finding. Right? The smallest, then the second is smallest, and so on. So if k is small, you can keep on doing that in order. Uh, so this is order kn time. Similarly, if I is equal to n, you can again do something like find max. Right? This will be order n. And if it is I is equal to n minus 1, this is the second max. This is again 2n and so on. So even if, right, even if, so here I should say I, if I is less than O log n, then you can do it fast, or if n minus I is less than all log n, then you can also do it faster. But these are not, I cannot give a generic, cannot give a generic solution for all k. This would be faster, right? So it depends on the value of I. Okay. So fine, we found two algorithms. One is just sort these and get ith element. This is order n log n. Second, find ith smallest or n minus ith largest element. And this is complexities. You can either take minimum of I times n or n minus I times n. Right? Minimum of the two. But in general, yeah. So the worst case would be order n square. Because in the worst case, it can be the median that you have to find. So it can be order n square by this case. Do we have anything else? Do we have any other solution for this? So if you recall, we did something with the heaps. So you can use heaps. And with the heaps, we know that if with the heaps, I can find kth smallest element. So we found an algorithm that works in order k log k, k log k time. And that looks very good, right? That looks very good. But I can see a catch already. The catch is that, okay, I am just given the elements. I have to create a heap. So I need to create a heap. So that will be On. And then find the kth largest. So this will be On plus k log k. Fine. So for small k, this is okay. But in the worst case, if you have to find, say, k is equal to n by 2, this will again be O log n log n. Right? So for small k, it is fine. But for large k, this is anyway going to n log n. So these are three things we knew. Now the main target of this lecture is, okay, can we do better, or in general, can I achieve a worst case linear time algorithm, worst case ON time algorithm for finding ith smallest element. Okay, and we will try to answer this question. So now again, so when we talk about order statistics, generally I'll really talk about two things. One is finding maximum and minimum, and second is general selection, finding any ith smallest element. Now, max and min finding is very easy, you know that. So if you have to find a maximum element, how many comparisons do you need? So I need exactly n minus 1 comparisons. So I always can declare max as a1 and keep on doing for I is equal to 2 to a dot length If AI is greater than max, max becomes AI, right? And then you return max. So I'm doing n minus 1 comparisons. Now this whole thing, you can compare it, you can think of it like a tournament. So think of it like a tournament. So tournament, there are say n players, and you have to find a winner. So what you are doing, you are keeping on uh, playing games. So and the smaller element loses. So as you have a game, so it's a comparison, and the smaller element loses. So for someone to win, so you see only one element can lose at a time, right? So only one element can lose in a game. So for someone to win the game, so for an element to win, n minus one elements have to lose. Right? So unless you lose, you are still in the game. So so that means there have to be at least n minus one games. So that means at least n minus one comparisons are required. Okay, fine. And same thing goes for finding minimum element. Finding the minimum element. That's fine. We knew that max and min you can do by using n minus one comparisons. But now, suppose I say that you have to find max and min simultaneously. And the question is, can you do better? So yeah, brute force would be find max by n minus one comparison and find min by n minus one comparison. So there are two n minus two comparisons, right? That is the naive algo we can think of. But can I think of something better than that? So actually, it turns out I can do that in say 3n by 2 comparisons only. How? How would I do that? So, so idea is that do not treat them as independent problems. Rather, you try to solve these together. So you have to do it simultaneously, and that is the thing you have to use. So what you can do? So you say you maintain max and min that are seen so far, right? Fine. So in the previous naive algorithm, what you were doing, you were also doing that. You were, but for each element, you're comparing with the max and the min. If it is larger than max, you update the max, and if it is smaller than min, you update the min. But now we are saying so. So for each element, so rather than comparing it against the current minimum maximum, so that would mean that two comparisons per element. You can process the elements in pairs. So what does that mean? So you see, I know what is the max and min till now. So I know this is my max element till now, this is my min element. And now you see I have next two elements, say AI and AI plus 1. And in the naive algorithm, what I will do, I'll compare AI with max and compare AI plus 1 by max and update if needed. Similarly, I'll compare AI with min and AI plus 1 with min. Right? So there are four comparisons in the naive algorithm. But now what can I do better? You see, among these two, because they are distinct, one of them will be larger. So if I know that, so first find out the larger among these two. And then I know that suppose AI is larger than AI plus 1. Then there is no point of comparing AI plus 1 with the max, right? Then uh, let AI be larger than AI plus 1. Then what will you do? Then compare AI with max and AI plus 1 with min, right? So earlier you were trying to compare both the elements with both max and min. Now you are saying you made a comparison between the two elements, find the winner. If AI is larger, then compare the larger one with the max and smaller than with the min. So how many comparisons now? So I did three comparisons per two elements. Well, that is interesting. So that way, if you do that, that means you have 3n by 2 comparisons. Okay. So yeah, this was interesting that you can do max and min simultaneously, and that will be helpful. Now let's go to the generic selection problem. So I am trying to do the selection problem. So till now we had uh, order n log n or order kn, order n plus k log k, these sort of algorithms. So can I do slightly better? So say I can do it. Can it? I do in expected linear time. Expected linear time. So as soon as you hear about expected linear time, there are certain algorithms where we talk about expected time, right? So you can think about, say, uh, Quicksort, where we got expected n log n time for sorting. Now, there is some similarity between what we do in Quicksort and what we want to achieve here. So let's see. So can we use a variation of Quicksort? What do we do in Quicksort, right? So you are taking an array, you take a pivot, and then based on the pivot, you divide this array into two chunks or two parts. This is less than equal to x, and this is x, and then you put x here, right? This is what you do in the partition step. So in the partition step of the quick sort, we choose a pivot and partition into two parts. So this is what we do. And then we recursively call quick sort. So you call quick sort here and call quick sort here, right? Now, with this much of recap of quicksort, now can you think what is something in quicksort that can be helpful? You see, what is good thing about partitioning step? So as a result of partitioning step, partition x comes in its correct place for the final sorted array. right? So let's say, let's say this less than x, x and get equal to x. Sorry, this is what we were doing. So less than equal to x, x and greater than x. So suppose this size is n1, this is n1, and this is n2. So n1 plus 1 plus n2 is equal to, and my problem is I'm using k. I think I am more comfortable with k. So I'm doing the kth smallest element, right? So I'm doing the kth order statistics. So what can you immediately say? Once you get this partition, after the partition, so I can say that okay, if k is equal to n1 plus 1, then pivot itself is the kth smallest element, is the kth smallest element. Fine, that is like okay, but yeah, that may not be the case, right? But what about if k is less than equal to n1? What would happen? Or if k is greater than n1 plus 1? So if suppose, so k can be anywhere, right, on this. So this can be k, this is easy, or k can be here. So if k is less than equal to n1, what would you say? So you would say that okay, my element would lie in this subarray only. Okay, and I don't need this array anymore. So if k is less than equal to n1, so we recursively find the kth smallest element in the left subarray. Okay, and similarly, if k is greater than or equal to n, greater than n plus 1, then what you have to do? It will be, so if k is here, it will be lying into this subarray. K is greater than n1 plus 1, and here k is less than or equal to n1. So it will be lying here. So that means you don't have to worry about this array, and you have to find k minus n 1 minus 1th smallest element here. So then you have to, so we recursively find the k minus n1 minus 1th smallest element in the right subarray. Interesting. So you're not doing sorting, but you are just using this partitioning routine of Quicksort to solve your problem. You say, okay, fine. Use a pivot, do the partition, and based on the final position of the pivot, you see if k is coming to the left of that, right of that. And accordingly, you go to either this subarray or this subarray, only one of these. So you are breaking your problem into a smaller subproblem. Now, okay. Now the size of the subproblem, so it depends on the sizes of the left and right subarrays. Okay. So suppose the partition was very good, and suppose uh, n1 and n2 both are roughly equal to n by 2. And then what would happen? You have to only go to one of the sub-area of size n by 2. So then, so the running time of the selection algorithm, so Tn would be T of n by 2 plus On. Okay, and if you will use, if you will solve it using your recurrence, so you will get this Tn as simply 1. That is quite easy. So you can actually just see Tn is Tn by 2 plus 1. You again replace it here. So this will be Tn by 4 plus On by 2 and so on. This will go to T1 and you get n plus n by 4 plus so on. So this will be 2n. So Tn On is very easy here. Now, oh great. So we got this linear time, or did we? So we only took the case when we got a very good partition. But what is the worst case performance? What is the worst case performance? So you see, in the worst case, it may happen just like it happened in Quicksort that you're not able to make good partition. So, so if in each recursive call, the size decreases just by 1. So then it will be Tn as Tn minus 1 plus 1. And if you solve it, that will give you Tn as theta n square. So, okay. So we had a hope from quicksort partitioning sort of algorithm, but what do we see? So in the partitioning based on quicksort, so worst case is theta n square, right? But if you try to analyze the average case, okay, that you can do very similar to how we did for quicksort, this comes out to be theta n, okay? And this you can also see from the case when the partitions are equal. That is similar to that. So, so theta n is the average case, but in the worst case, it is theta n square. And just like in the quicksort, so you see, if we can ensure that every time the partition, the new sub problem that you get is a fraction of the original problem. So, so if we can find a constant, and it can be large, say, 9 by 10, that is smaller than 1, such that Tn is less than equal to T of that constant 9 by 10 and plus On, then also it is fine to prove that Tn is On in the worst case. So Tn becomes On here. It's only when we can't find a constant, when we say Tn is Tn minus 1 plus On or Tn minus some constant k plus On, that we get On square. But if we can ensure about this particular constant, then we can get Tn as 1. And that would help us in getting a worst case linear time algorithm. So now, essentially our target is, okay, can we find a way to ensure that my sub problem reduces by a constant factor. Constant factor, but not by a constant number, but constant factor every time. Okay, and that is what gives rise to a very interesting problem for this selection or order statistics. So what we are saying, so the partitioning that you do, so partitioning may not be equal, but it may be skewed, but we should be able to throw away some a fraction of the array in each recursive call. And if we can do that, then we get a linear time algorithm. And it's worst case. So a very good algorithm for doing that, to making sure that every time you throw away a fraction of the array, was designed by Blum, Floyd, Pratt, Rivet, and Tarjan. So they gave an algorithm for this. And the, the nice part about this algorithm is the way they select the pivot. So the interesting part is how they select the pivot. Okay. So yeah, before I talk about the algorithm, what essentially they are able to achieve. So every recursive call reduces the size of the array at least by 3 by 10. Okay, this was more than what we were wanting, even if it reduces by 1 by 10, like x to 9 by 10x, it was fine, but it says initially x to 7 by 10x every time. Okay, fine. So this is what it does. But finding the pivot requires another recursive call on an array of size n by 5. Okay, so if there are n elements, you have to make another recursive call of on an array of size n by 5. So together, we see even together, this is like, okay, this is roughly 7 by 10 n, and this is uh, 2 by 10. So together they are 9 n by 10, and that is still less than n. And that is what helps. And that is what we will see. So how exactly are they able to achieve that? Fine. So let's now talk about the algorithm. So we are starting with A. So A is an array of size n. So let's take an array of size n. What they do, they say, so you break A in n by 5 groups of 5 elements each. Of course, except the last one, which would have between 1 to 4 elements. So then may have. Yeah, it can also be n may be divisible by 5, so then it is exactly 5, but otherwise it will have at least 1 to 4. So you have, so think about some grouping here. So you have G1 say with 5 elements, G2 with 5 elements, G3 with 5 elements, and so on. And the last one would have some elements between 1 to 5. G of n by 5. Okay. Sure. So here I will just expand it a bit. So here, so each group GI has 5 elements. Okay. Fine, I can do that. I can do that in linear time. It's all right. Okay. Now, next. Then they say, so now you compute median of each group. So compute median in each group. Okay, is that easy? Yes. So take any GI. So computing median means uh, there are 5 elements. You have to find out the third smallest or third largest. So you can do it. Fine. So you can do it in some constant time. Uh, and there are n groups again. You can do it overall for in constant. I mean in linear time. So all the n by 5 medians can be computed in O and time. Fine? Sure. So because even if you take an n square algorithm, I think even if you take an n square algorithm for sorting it individually, right, this is all right. So you can get, because n square here is n is 5, so overall you will do it in 5n, but you can get a more efficient algorithm than that. So yeah, so you can do it in O and time. Fine. Okay, starts looking interesting. So now what you are saying, you have median 1, median 2, up to median n by 5. Median I. Okay. And this is what I have. For each group, I have a median. And each individual median is larger than 2 elements and smaller than 2 elements. Now that's where now the interesting part comes. You see, remember the recursive call? So now you they say, now recursively call the algorithm. So you see, you don't have the algorithm yet. They are saying, okay, suppose you have the algorithm, you recursively call the algorithm that could find any ith element. That could find any ith element. Yes, so you can use it to find the median of these n by 5 medians. So recursively call the algorithm on this array of medians and obtain the median of medians. Okay. And call this element x. Okay, you're calling the algorithm on this array of medians, so the n by 5, and getting an element x that is the median of medians. And now you take x as the pivot for the partitioning algorithm. So remember what is the partitioning algorithm? You take an array. Remember, this is the quicksort partitioning. So you take an array of size n and you have to partition into 2 parts and you have to take a pivot. And generally we used to take the first element as the pivot. Now you're saying no. You use an interesting way of, interesting algorithm. You find the pivot x and break into 2 parts. So you will get x less than equal to x and larger than x. Yes. So use this procedure for taking the pivot, choosing the pivot, and then partition. So fine, okay. Right. So now you have a generic question. Okay. So what? So is X a good choice? So a good, whether it a good choice or not, will depend on whether it helps in reducing the size of the subproblem. So can it help throw away a fraction of elements every time? Okay. Sure. So there are, so X came from an array of medians, right? So they were n by 5 medians. So if I just do loosely and do not talk about these ceilings and all, uh, so I can say that at least half of them, so and because you are taking a ceiling, are less than x, right? So at least these many are less than x. Okay, and this looks like in roughly like n by 10, right? Roughly like n by 10. So roughly n by 10 of the medians are less than x. Fine. Now for each of these medians, each of these median m, let's call it m, that is less than x, I can further say there are two elements that are less than this median because this is a median of 5 elements. So m is a median of 5 elements already. So 2 are less than m and 2 are greater than m. So in its corresponding group, so each of these median m, the corresponding group, it contains two elements less than n, and because they're less than n, they are also less than x. Okay, and that's what makes the mass. Okay, so that means the number of elements of A that are less than x is now getting equal to 3 times the previous quantity n by 5 by 2 minus 2, and this is getting equal to 3n by 10 minus 6. So there are at least n by 3n by 10 minus 6 elements that are greater than x. Okay, and now I can make a symmetric argument for elements that are less than equal to x. So, so by a symmetric argument, number of elements that are larger than x are also greater than equal to 3n by 10 minus 6. Okay, so then what are we saying? So I got x, and if I choose x as pivot, So number of elements in both the partitions are, they are greater than or equal to 3n by 10 minus 6, or they are less than or equal to 7n by 10 minus 5 plus 5, sorry, less than or equal to 7 by n by 10 plus 5. So, so if I take the larger among the two, so the second recursive, so the recursive call would be made to either this array or this array, and the larger among these is 7n by 10 plus 5. Yes. So the next recursive call is made on a subarray of size less than or equal to 7n by 10 plus 5. Okay. Fine. But this required, so you required a recursive call to find median of n by 5 medians. Right? So this is less than or equal to n by 5 plus 1. So Tn, so overall the complexity of this algorithm is, you made a recursive call for n by 5 plus 1 elements, plus this is to find the pivot using the same algorithm. Find the pivot as the median of medians, plus you make a recursive call now on the array 7 and 10 by 10 plus 5, and plus you do some ON operations to find median of all the medians and so on. Okay, and this together you can do a substitution and prove that, so this Tn is actually ON. So that means by this algorithm you can solve kth order statistics in worst case linear time. Okay, so yeah, so just to summarize what you do, you actually use quicksort partitioning based algorithm. That is, take an array A, choose a pivot and X, and based on X you partition, and then you see the two things n1, n2, and if see this index, if k is equal to n1 plus 1, answer is X. If k is less than n1 plus 1, you recursively go to left, or if it is greater than n1 plus 1, you go to right. Now what you do interesting here, so you say okay, choosing a pivot by taking median of medians, divide into n by 5 groups, get median of each, and take their median by a recursive call. Because how do you find the median of n by 5 elements? You have to go back to the same algorithm. So you do recursively, use the same algorithm that you're developing. Okay. So that's how you find a pivot. And once you find a pivot, you are guaranteed that, so n1 size and n2 size both are greater than or equal to 3n by 10 plus 6. Or analogously, they are less than or equal to 7n by 10. This was uh, minus 6, and this is plus 5. So that means the sub-array where you will go will be less than equal to 7 n by 10 plus 5. And that is where you established, okay, TNH, you do this, median medians. So less than equal to T of n by 5 plus 1 plus you do a recursive call. So T of 7 n by 10 plus 5 plus you do some ON things like, okay, you're doing this whole partitioning and you are finding medians of n by 5 groups. So they are all ON. And this overall gives TNH ON. Okay, so that is a very interesting algorithm and also gives you a handle that yes, I can find order statistics in ON time. Okay, so that was all we had for this week. Okay, thanks.